Ermin, are we ready? Okay, so thank you everyone for joining the last SNAPP seminar of academic year 2023 and 4. So I'm excited to have Ermin Wei, my colleague at Northwestern, to speak to today. So Ermin is an associate professor in electrical and computer engineering and industrial engineering and management sciences and by Curtis Computer Science at Northwestern University. She's received her PhD and master's from electrical engineering and computer science at MIT. And her team has won second place in the GO Competition Challenge 1, which is the electricity grid optimization competition organized by Department of Energy. So Ermin's research interests include distributed optimization methods, convex optimization and analysis, smart grid, communication systems, energy networks, and market economy analysis. And in particular, today, Ermin will tell us about various aspects of federated learning. So without further ado, the floor is yours, Ermin.
Thank you, Changhan. Thank you for the introduction and for the invitation. It's my great pleasure to be here as part of the SNAPP seminars. Maybe before I start, how do you usually handle questions? Is this through chat or people just unmute and ask?
It's whatever way you would like.
Okay, so I would rather people ask questions right away rather than wait to the end, especially if it's notation clarification related questions. So feel free to unmute yourself and just shout. I will try to keep an eye on chat, but if I miss it, please just unmute and ask. Okay, so actually, I realized that Changhan just read a long list of my research interests, and I'm not talking about optimization or smart grid here, right? But it's all related. So I'm going to be talking about federated learning, generalization, heterogeneity, and incentives, and I'll kind of give you the background story of how we got here, given all the research interests that Changhan just mentioned. And this is 3 pieces of joint work with my great collaborators. I'll introduce them as we go along to each individual pieces. So let me go ahead and get started. So let me first set up the federated learning, right? It's this kind of a server client architecture with a server in the middle and a bunch of clients on the side. So here, for just setting up the notation, we're going to assume we have K clients, and each of them has access to its local data. And each of the clients, because it's local, they have potentially heterogeneous data distribution, and they might also have different amounts of data, etc. So the goal is to collaboratively optimize the this function right here. I'm not sure if you can see my mouse, so let me circle this one right here. Right, so you can think about, we're going to put this in the machine learning framework, and then, or the baby version of that, let's just do empirical risk minimization. And you can think about these little FKs as a local loss function that's local over all the local data batch. And then we're going to add up over all the agents from 1 through K. So, and for people came from distributed optimization background, this is a special case in which we're looking at just the star graph where there's a server in the middle and clients on the side. And so I'm going to be focusing on federated learning for this talk, and I suspect a lot of these results would generalize to distributed optimization setting as well. But for today, let's just focus on FL. Okay, so now let me hit to the first part of the talk, right? So I'm going to be talking about generalization and data heterogeneity. This is based on a joint work with 2 of my students. Zhenyu on the left, he's the now 3rd year PhD student, and then Xiaochun, she just graduated, and she's will be joining Duke for a postdoc. And this is based on a AI stat conference paper, and so it's kind of still ongoing, right? We have a conference version out, but Zhenyu has been working on tightening the bounds over a weekend. I think there's some newly developments between when I made the slides and now. So, but anyways, I'll give you the preliminary version for now. Okay, so how did this work get started? Think about polar bears. Okay. So forget about the federated learning for a second, right? So that can capture a lot of different setups. So in particular, this all started when my collaborator and I were talking about sensing network out in the Arctic to monitor polar bear habitat. So we're going to measure different climate parameters and kind of use that to predict how much polar bear activity we're supposed to see. So why is that important? So because that is not, if we think about polar bears, that's not something someone will see on a daily basis. So there is a limited amount of data, right? And also this is a perfect test bed for federated or distributed algorithms because they have very limited connectivity out there in the Arctic. And also they have a lot of constraints on the hardware, like how much power they can provide, how much communication, computation they can afford, and so on. But for today, let's just focus on the data part, right? So my collaborator and I started talking about polar bear, and I say, hey, I have all these wonderful distributed optimization algorithms you can use: first order, second order, synchronous, asynchronous, etc. So we all know that literature is huge. And then turns out they said it, and some of the methods would converge faster than the others. Right? But then the collaborator told me it doesn't really matter how fast it converges, right? Because we're monitoring polar bear. They are not running at like 3.5 gigahertz level. You can't afford to run multiple updates between when you have a polar bear sighting to the next. You can't afford to take a very, very long time. So the optimization algorithm in terms of speed performance is not very crucial. What is crucial though is this model supposed to perform very well on unseen data because they have very limited amount of data they have access to, and they want to train a model that would perform well, right? So but then in the machine learning context, that's called generalization, and we aim to build a model that would generalize well. Okay, so then we started kind of formulating this. I mean, it's a well-studied problem, but let me just set up my notations here so we're all on the same page when we talk about this generalization. All right, so what you really want is to minimize this population risk. Still, we're talking about like a empirical risk minimization framework. So there is the loss, W is the parameter we're trying to learn, Z is the data, and it's coming from some distribution P, and we're supposed to minimize this expected cost, which unfortunately we don't have access to because P is the underlying population risk that we only have samples. Okay, so I'm going to call W star the true minimizer of the population risk. You can think of that as the ground truth. What we have is some sample set S drawn from that distribution P, and then we will aim to minimize the empirical risk. So I'm going to use F for the empirical version of that. And essentially, instead of expectation over distribution, I'm just going to take an empirical average, right? So I add up over different samples and trying to aim to minimize this F of W instead. And the generalization generally refers to the gap between these two objectives. One is based on the empirical observation. Another one is based on the population distribution that we don't have access to. Okay, well, okay, as I said, this problem is fairly well studied, right? But let me just give you some I guess visualization to see how far off things might be. And keep in mind, again, polar bears have finite, very small, right? Finite training sample set. So we're going to have a finite training set that's drawn according to P, and then we're going to run some stochastic algorithm A. So think about stochastic gradient descent, for instance. And when we take expectation over A, that means we take expectation over the different stochastic gradients, the stochasticity from the gradient samples. Okay, and then once we have this algorithm and the data set, we will generate a model. We're going to call that AS, and that's a function of S of the sample. And generally, W star is not equal to A of S. That's because of the difference in distributions. And as you can see here, right? So this is a standard normal, is the red line, and I draw 100 data sample from standard normal. Even though we have concentration resultants that puts us as n goes to infinity, the histogram and the red curve is supposed to be exactly on top of each other, or it gets very, very close to each other. But for finite sample n, they are different. Okay, and what's more bothering for me, right? So I'm used to think about proving optimization algorithm performance and generally saying, if I take expectation over some gradient step over all samples over different stochasticity in the gradient, I should be able to recover the true gradient. Okay. That's like one of the key steps a lot of these stochastic optimization algorithm uses to prove convergence. So once we are given a fixed sample set S, there's something fishy about that statement I just made, right? Because all that I could, even though I am going to generate stochastic gradients, I'm going to sample based on this blue part, the histogram. I start with the blue histogram, I will only have access to the blue histogram. I will never be able to sample from the true red line distribution over there. Okay, so this is the distinction we want to make, right, between this kind of finite training sample-based federated algorithm versus the conventional one, which says even though everyone has a finite set of distribution, the data, you might still be able to sample from the original distribution every once in a while, or maybe infinitely often, right? So it says every time. So the alternative setup is to say every time I will use a small data batch, but every time that batch is drawn independently from the underlying data distribution. Right. As a result, if you do that, then it is fair to say if you take expectation, it's going to recover the original gradient. Whereas here in the polar bear setup, we have very limited data to start with, and we will always have that set of limited data. I mean, it might grow a little bit over time, but let's say we actually wait until we have all the data and then started running algorithms. Then we were stuck with this blue set. And so different iterations in the algorithm, right? They will have some correlation based on this S. Okay, and that's what makes the analysis slightly involved and I think very interesting as well. Okay, so, well, what is our goal, right? We want to study the difference between the performance of the true optimal solution, which is a W star, that's a population minimizer, risk minimizer, and A of S, which is what our algorithm would output based on this given data set S. And then, so E here is the population risk, and we're trying to, then we'll take the expectation over stochasticity of the algorithm and also over different data sets. So this is the excess risk, and we're going to decompose this into the following 4 parts. The red part is what I will be focusing on for the rest of the talk here. We're going to call this the generalization error, and in particular, it talks about the performance. I'm missing a parenthesis here. Sorry, the performance of the algorithm output evaluated against the population risk versus the algorithm output evaluated against the empirical risk. Okay, and then the second part is epsilon optimal. That's essentially says how good your optimization algorithm is, right? So if you have a good optimization algorithm, oh, sorry, I forgot to introduce. W hat is the empirical mean. So the true empirical minimizer, assuming you can solve the empirical problem exactly. So if you run a reasonable optimization algorithm, this distance should go, the blue part should shrink as you run more and more iteration of the algorithm. The third component here is the difference evaluated by the empirical risk between the empirical mean and the population mean, and that's always less or equal to 0 because the definition of the empirical mean. And the last term is the difference between empirical versus population evaluated at the population mean, and the expectation that should be 0, right? Just by definition of expectation over the sample set. Okay, so but because we have these 4 terms, and in order to bound the left-hand side, right, and we know how to deal with the blue part and the other 2, one is non-negative. So essentially, if we can get a good upper bound on the red term, then we should have a good bound on the overall risk. So as a result, we're going to focus on the epsilon gen, the red part there. That is what we're going to call the generalization arrow. Okay. All right. So with that said, right, so what is difficult? well, I already hinted on this, right? Essentially, because both the F, which is the empirical loss function, and the S, the sample set, depend on the sample set, right? And they are not independent. Therefore, this the two parts, one is based on the population risk, one is based on the empirical risk, right? So if we look at this, there's also this algorithm A that explicitly depends on this sample set S. Okay. As a result, if we want to invoke as many of those existing concentration bounds, they assume independence when we start drawing samples. And as I said, I start with a finite set S, right? The blue part. The more sample I draw, I could draw more samples, but they're all going to be based on that histogram, which is not the same as the original underlying true distribution. So condition on S, that's why I have a question mark here, right? In general, this part, they are not necessarily equal to each other once you are given the finite set of samples. Okay, and this is again a contrast to how we typically prove optimization algorithm, which is when you take expectation, you imagine the empirical gradient is going to be the same in expectation as the true gradient point. Okay, so that's really the subtlety where that's coming from. We start with a finite set. Therefore, all the samples you can draw is based on that particular set, and you would not be able to claim things like in expectation our gradient the same as a population-based gradient. Okay. All right. So then what do we do, right? Obviously, as I said, generalization is an important task, and people have looked at this from various angles. So one line, and by the way, so far I've been talking about the centralized setting. I'll talk more specifically about the distributed setting a bit, but the same concept of generalization appears in both centralized and distributed case. So in the centralized case, what people have been looking at is this concept of uniform convergence. That is essentially to say, instead of taking expectation over A and S, right, which is kind of difficult because of the dependency of A of S and also this F function both on S, we're going to just take a soup. Right? The dependence comes because both F and A of S depend on S. So if I get rid of one of them and then take expectation, it becomes much cleaner. So instead of A of S, I'm just going to plug in any W here, right? Any parameter or any model we learn, and going to bound the soup difference. Okay. So again, the generalization we're stating here is a difference between population risk versus empirical risk evaluated at this A of S. But here we say, let's forget about particular A of S, this point, just evaluate over all potential points and take the soup. That is clearly an upper bound. Right. So good news is, now we got rid of A of S, it's just E and F, and then when you take expectation over S, right, over all the samples, then you can invoke these concentration inequalities, and you can get reasonable bounds, and they sometimes lead to bounds related to VC dimension and Schwarzmacher complexity on the model space. So this is the one line of work. The good thing is we are able to now bound things properly. The bad news is sometimes these dimensions or complexity can be very large, right? And I mean, these are epsilon bounds. We expect them to be small and meaningful. Once they're really large, then they are not very meaningful. And I think another criticism here is because they got rid of this A of S, the bounds became independent of the algorithm. Right. So again, I kind of started this line by talking to the sensor deployment guy. My collaborators, they wanted to figure out what algorithm is the right one to deploy in this particular setting. So could we somehow figure out how this epsilon gen or generalization error depends on different kinds of algorithms, right? Does that even make any difference, right? Other than the convergence speed, does that affect the generalization? Okay. So alternative approach in the centralized setting is the stability-based line of analysis. So stability, in a rough sense, measures how the algorithm output changes when we perturb the training data. Okay, so it is saying, so think about it as an input into the algorithm as a sample S, and the output being a model. Now I'm going to perturb the input a little bit. How much is the algorithm output going to change? Okay. In particular, we're going to adopt this uniform stability measure proposed by both Kidd and Ellis in 2002. So it's a while back. So they're saying algorithm A is epsilon uniformly stable if I can take any S and Si, such that so the difference between S and Si is exactly by 1 point. I'm just going to change 1 point. And then I will measure the difference in loss functions. When I look at the output of the algorithm based on S and the output of the algorithm based on Si, I look at the loss function differences, and if that's bounded by epsilon, then we're going to call that epsilon uniformly stable. Meaning essentially, when you perturb the input into the algorithm a little bit, the loss overall does not change too much. Right? And remember this generalization error we're trying to measure is how much difference there is between empirical versus population. So if you can perturb the data a little bit and the loss doesn't change, then then after some math, you can show the difference between the empirical and population is also bounded by epsilon. So the same epsilon. If the algorithm is epsilon uniformly stable, then that is also an upper bound on the generalization. Okay. So this notion kind of perturbing one data sample, it might appear a little strange, right? Why is it enough to just perturb one? So so let me just say this also reminds me of how the epsilon delta differential privacy is defined in I guess computer science and a few other communities. They also perturb things by 1 point. And I think it's related, and also it's also related to the LOO leave one out notion, where you kind of take 1 point out and then look at the rest. So the key insight here is after we take that point out, right? Then if you look at expectation over that 1 point, then these two things become independent, because you took one out and you could have taken anything out, right? And if you take expectation over that, you kind of get rid of the dependency on the same data sample I was talking about before, right? So that's the idea. You kind of perturb one of the input sample set. As a result, you gain in the independence, and that later on carries over to the analysis to kind of simplify it. But that's my hand waving argument, right? I think really the rigorous term here is to kind of this way we can get the expectation over the algorithm, right? We will leave the algorithm part in there. Remember previously we were saying the uniform convergence actually got rid of A and S, both of them. So by doing this stability, we managed to keep this dependency on A inside the definition. Okay. All right, and also I think it's kind of natural to say we're going to look at a perturbed version of the sample set when we keep in mind that our overall goal is to look at the difference between sample versus population, right? Empirical versus population. So when we perturb, it's almost like we're going to resample from the population. Okay. All right, so now let me dive into the federated learning setup. So everything above on generalization is what happens in the centralized domain. Right. So we managed to introduce this concept, or that's in the literature, the concept of uniform stability that looks at dependency on algorithm. But what is still missing is the dependency on local data distribution. Okay. So in federated learning, as we said in the beginning, you imagine a bunch of different agents with local data samples. So, and in the polar bear study again, depending on where you put it, you might get very different distributions. Right? And does that affect the generalization? Right? Should you try to position them so that you mostly get the same distribution, or would you be better off kind of collecting things from very different distributions? How does that affect the generalization? Okay. So once again, we have K agents, and I'm going to introduce this SK as the subset of samples at agent K, and they're going to draw from local distribution PK, and this might be different from the overall population distribution. And we aim to minimize this objective, which is just the weighted sum of the local loss. And the n, little n, will be used to denote the total number of samples. And K is the number of samples at agent K. and S is the union over all this local sample set. Okay, so with that, let me do a quick review on what is out there already in the literature, right? So in the centralized case, we actually reviewed a bunch of them already. There is also something known as the accuracy robustness trade-off, and people have looked at that. So then there's also work on uniform convergence stability analysis based on federated learning algorithms. But they have not looked at the explicit dependency on data heterogeneity. Another very interesting and closely related line of work is my second bullet here. It's on generalization bounds on heterogeneous data. Right. Except they start with infinite sample points, meaning they allow the gradients to kind of go back, resample from the population. And that is one of the early equations I had, which is to say the in expectation, the gradient, the empirical sample, the gradient is going to be equal to the population gradient. So that's what I mean by infinite sample points. Sorry, I see there's a question. Why is PK equal NK? All right, okay, let me go back. I think there's a question about this, right? So in the chat, there's a message saying, why is PK equal to NK over N? This is just one way to put it. You can figure out other ways, right? So this way, we kind of say we're weighing every single point exactly the same, but you don't have to do it. So this is just one of our versions to weigh the different data distribution. You could also think about this weighted by different weights, and then your population distribution would also be a differently weighted version of the PKs. I hope that clarifies. Okay. All right. So let me keep going. So the existing literature either looked at centralized case or distributed case or the federated setting with infinite samples, or there were not explicit dependency on data heterogeneity. So here we want to be able to characterize the explicit dependency on data heterogeneity under this finite sample domain, right? Under the polar bear setting. So all right, so how are we going to do this? We're going to adopt the uniform stability notion here, and then we're going to perturb it a little bit according to the on average stability. So again, we're going to introduce two neighboring data sets, and these are the data sets that's offered by exactly 1 point. So I have this SK and SK prime. Oh, and by the way, I'm only going to pick one of the agents to perturb, keep everyone else the same. So take K first, and then pick one of its 1 through NK points, and I'm going to perturb it. I'm going to perturb by resampling from its local distribution. So this ZKJ will be different, potentially different from the original ZKJ prime, might be different from the ZKJ. Okay, and then we're going to call this federated learning algorithm to be epsilon on average stable if given any two data sets where I'm only perturbing as one of the K agents, one of its data. After all these perturbations, if I can bound the expectation of this loss function by epsilon, then we're going to call this on average stable. And if the algorithm is on average epsilon on average stable, then that epsilon also becomes a bound on the generalization error. Okay, so it's very much related to the previous setup in centralized case. The only difference is here we're going to take a max over J, or you can think about this inequality holds for all J, meaning we can pick any of the data points, and also there's all K here, so I can also perturb for any of the K agents. Okay, all right. So I think I've thrown enough notation at you, probably a little confused. Now let me recap a little bit. There are kind of two notions of stability here. And this is not to be confused with the uniform boundedness before, right? So that one gets rid of the A dependence completely. Here we're keeping the A in the loop. And the uniform stability introduced before takes the soup over Z, I, and S. Whereas the on-average stability, what else did we do? We kept the expectation over S inside rather than taking a soup over S. Okay, and why do we want to do that? once we take expectation over F, then we take the distribution into account. Whereas if you take the soup over F, then you're just going to take like a max over the entire distribution, and you kind of lose the distribution dependency here. So for us, it was crucial to keep this S here as part of the definition for stability, and we managed to show this is also an upper bound on the generalization error. Therefore, moving forward, based on this on average stability, we will be able to kind of give you the explicit dependency on data heterogeneity. Okay, so then what are we going to do? So far we've introduced this notion of epsilon on average stability in federated learning setting. And then we're going to take three of the very popular methods, FedAvg, SCAFFOLD, and FedProx, and analyze their performance under this stability measure. Okay, so this is how a federated learning algorithm usually does things. There are the server and the client, two parts. The clients will each individually execute some local computation, and these three different methods correspond to either do local gradient descent or stochastic gradient descent. One scaffold takes a gradient, stochastic gradient plus the variance reduction term, and in FedProx, there's a prox term. So I'll have more math on the next slide. So after some local steps here, the clients will report up to the server, and server just aggregates, usually just takes an average, and then broadcasts out the new model and kind of iterates like this. That's the general architecture of federated learning algorithms. And then in particular, if you want to see the math, here it is. So in FedAvg, right, they take you can take tau I local steps of local gradient descent, could be stochastic gradient descent. In SCAFFOLD, you take the local gradient and also take the difference between local versus global gradient to take care of the variance reduction term. And then lastly, in the FedProx term, there is this proximal term. So for both FedAvg and SCAFFOLD, we allow the agents to take local steps multiple times before you report back. And FedProx doesn't matter how many steps, it's the same thing, so just take one. Okay, and then comes more math. So on a high level, don't spend too much time parsing through here. Let me just walk you through. On the high level, we are going to assume some standard conditions on the loss function. They have to be Lipschitz continuous and smooth. The variance between sample each individual sample one and the empirical one is going to be bounded. So we're not assuming it's bounded away from the true population one, but the empirical one. And then, so if we look at the iterates, right, we're going to be able to bound. Now, okay, here's the part that might be a little confusing for people who came from optimization. We're not looking at the distance to optimal solution. We are looking at the distance between two trajectories, generated by one based on sample S, one based on perturbed SK. Okay, so this WT minus WT prime, these are the distance among these two trajectories that I start the same initialization, same everything except one data in the training set, and then I run the algorithm. How far we expect the distance to be, okay? And then we can bound these for FedAvg, SCAFFOLD, and FedProx. So let me actually go to my next slide that I have more color coding to explain these. So let me just talk about one of them, FedAvg. So ignore the constant. The alpha betas are dependent on the step size. And so the first term here, L is the Lipschitz constant, I forgot to mention. So dk here is the total variation between agent K and the global distribution. So like a weighted sum of all pks. Okay, that's what my p is. And the second term, you can think about that as the optimization progress, right? You're essentially evaluating the norm of the population risk evaluated at these iterates. The last one is related to the sample variance based on the gradient sampling. Okay, so there's the red term that depends on dk. That's our reflection of heterogeneity, how that plays a role here. And one based on optimization and one based on variance. So now let me go back to the previous slide, and you can see they all have the same flavor here. Now there's one term based on dk for each of these three algorithms, one based on the algorithm progress optimization, and then the last term based on this epsilon, which is the variance in the gradient. Okay, so all right. So this this is good in the sense that it gives us an explicit bound, right, related to the heterogeneity in the data distribution, based in the particular in the total variation between local population and the true global distribution. Okay. And what is not there is I just tell you the bound between WT and WT prime, right, which is distance between these two trajectories. But what I really care about is epsilon generalization, which is how they would perform against the loss functions. So that's what this slide is for. So essentially, you kind of plug in the results from the previous slide and do a little bit more math, and you get to this one. So everything so far is under the convex case, where we were able to use constant step size. And here, so again, they have these three terms. The first one is based on this D. So here, instead of DI, we're looking at D max, which is the maximum between all the DKs. So the maximum total variation between local versus global distribution. The second term here is related to T or delta zero. You can think about this as the optimization progress. Okay, and the last term is related to sigma, which is the sample gradients variance. Okay, so overall, we were able to kind of characterize this epsilon generalization arrows dependency on the data heterogeneity, and it really matters, right? So as you can tell, the higher this D max value will be, the larger at least this upper bound is. Okay, and what else is interesting is these arrows, right, all kind of grow as T increases, which is, again, don't think about optimization. Okay, here we're really talking about generalization, and this is essentially overfitting, right? As you increase T, when you take more and more steps, your generalization bound at least gets worse over time. Okay, which in some sense is, you can think about like running an optimization for a very, very long time is especially in neural network, it's almost like you're memorizing the data input, right? Once you memorize it, it becomes worse for generalization. So which actually guides me to the non-convex case, which we're talking about neural networks, right? So we also have kind of similar results on the non-convex side. They have the same flavor. There's a red term, which depends on D max, the data heterogeneity. Generalization becomes worse when data is more heterogeneous. And also another term based on D0, which is the optimization arrow. Then lastly, also a term based on sigma. Okay, and then I skipped one slide. Let me come back here. You might be wondering how tight it is. Actually, I think some of the term might not be tight, but we managed to recover the state of art for at least when D max is equal to 0. So when D max is equal to 0, then a lot of these kind of collapses into centralized case. That means everything is IID, right? Your local distribution is the same as the population, the same as the overall distribution. So then FedAvg becomes SGD, SCAFFOLD becomes Saga. And the literature out there that we could find says the SGD with constant step size has this rate T over N, right? And when our D max is 0 here, our upper bound actually collapses to on the order of T over N as well, with a few other terms that is smaller than T over N. Okay, so in that sense, we're pretty happy with the bound. But again, it's just an upper bound, right? We managed to recover other upper bounds in the literature. Now, how close that is really to reality is another question. I guess as a partial answer, we do have some empirical successes in reproducing the trend in our upper bound. So we took a few kind of the machine learning made up samples to try here, and we tried our FedAvg, SCAFFOLD, and FedProx here on the top. So going to the right is where the data heterogeneity increases. And what we're plotting here on the y-axis is the absolute value between testing and the training loss. So what our epsilon generalization measures. And as you can see, as we increase the heterogeneity, you do see upward trend. Okay, so not just the upper bound increases, but the actual empirical evidence supports that. And going upwards is where, I don't know if you can read this, different training losses. And the top one has the smallest training loss, the bottom one has larger ones. This is where we stop the algorithm. So you might stop the algorithm early when you're at 0.2, and this difference between training and testing loss actually is smaller than if you train the algorithm longer. So this kind of supports our increasing in T theory. As you train more, your generalization becomes, at least the epsilon gen that we're measuring becomes worse. Okay, and then lastly, this bottom right plot plots the FedAvg under different step sizes, and you can see the smaller step size tends to have better generalization because you're taking more conservative steps every time, and like when we fix the same number of iterations. Okay. All right. So with that, I will finish my first part, and so we talked about generalization bounds on federated learning, and we were able to characterize the dependency on data heterogeneity. Okay, so now, I do have two parts, but with the time, I think I will only talk about one of them. But let me just say briefly, I am now going to move away from optimization, generalization, and polar bears. Now think about iPhone users. Okay, I'm going to talk about incentive design in federated learning. So this is a joint work with Men Zhang. He was a postdoc in our group and now is in Zhejiang University UIUC Institute in China, and also with my colleague here, Randy Berry, in the ECE department. Okay, so, all right. So why are we switching context? Okay, we're talking about now iPhone users with Siri enabled, or if you have Android, think about Androids with Google Keyboard, Gboard. Okay, so here and each of the devices become one of the clients in this federated setting. Okay, why is that? Because now as an individual owner, I might have incentive to either join or leave the system if I choose, right? I can maybe uninstall certain apps if I don't want to be part of it. So I could be strategic, and I could try to get out of the federated learning algorithm. So this is different from the polar bear one, where we design everything, right? There's some engineer design the whole system, put it out there, and everything is working as planned. Here, we're dealing with strategic agents. Okay, so the agent serves two roles. One is they will try to implement the algorithm if they wanted to. Two is they might also have the different preferences over the particular outcome. Right. So again, think about iPhone and Siri. So Siri responds to you well if you have a average accent, but according to the data that it's trained on. Whereas if I have a super weird accent and I try to talk to Siri, she might not understand me at all. Right. So in that case, do I want to join? Maybe I want to leave the system. Okay. And then due to time limits, I'm going to move a little faster here. Right. So essentially, the setting here is we're going to look at this kind of non-IID data. Right, so maybe I have cats only, and another one has cats and dog, or maybe I have a very weird accent and the other one has an average accent. So how do you design federated learning mechanisms so that you would keep the different users in the system? Okay? Now you might be wondering, if they're so different, why do I want to keep all the users in the system, right? So it could be because everybody has a little bit weird accent and they only have a little bit data. By aggregating across all, you actually train a model well for an average accent, and also you aggregate the data. Right? If I opt to leave the system, then I just have my little weird accent with tiny amount of data, and that might not be enough. Right? So we saw previously the generalization actually depends on how much data you would have. Okay, so there some literature here. So there are a lot of work on federated learning algorithms. I think we talked a little bit about that already. So what's different in the second part is we're looking at the mechanism design. How do you design the right incentives to keep users engaged in the process? And we're going to be proposing a faithful federated learning algorithm based on what's called as a VCG mechanism. So let me maybe just kind of briefly show you what the math would look like, right? So again, we have the expected, the population one is E, the empirical one is F, and the notation is pretty much same as before. And the server goal is trying to minimize the empirical global loss, which is the weighted combination of the empirical losses based on the local FKs. And each of the agents may choose to leave the system and just try to minimize its local FK. All right. So what would each of the agents want to do in real, if they could choose, right? If there's a magic wand, they would want to minimize this EK, which is the empirical loss based on local population distribution. They actually don't care about how it works globally, right? When I talk to Siri, I just want she understand me. I don't really care if it understands any other people. Okay, so what we measured in this work is the distance, right, between, so EK is the population risk based on local distribution K, right? So the true risk agent K may experience evaluate at 2 different points. One is W0, which is what the federated system would output. One is the true minimizer. And another pair here, down here, is when we measure the distance between what you can get by doing local training versus the true minimizer you're trying to get. Okay, so really each of the local users should try to compare these 2 values and pick the minimum one. Right? If I'm better off doing training by myself, I should do that. If I'm better off doing training and joining this federated system, I should do that instead. Okay, so then we managed to use this Hofstadter inequality to bound these 2. And then, so something interesting happens, right? The first bound depends on N, the total data available in the overall system. And also, so this is somewhat related to my DK from the previous part, right? The distance between local distribution and the overall system distribution. And then the bottom part, which is what would happen if I train by myself, that depends on how large this NK is, how many data you have. Okay. And the moral of the story here is if I were an agent with a lot of data, I might just choose to opt out, right? But if I am a little agent, if I'm an agent with very little data, then I would try to join because the population one has the the summation of N on the denominator, right? And if I am an agent with a very weird accent, I might choose to leave the system. But if my accent is on average, right, then I would try to join the system because the distance is small, the second term up there. Okay. All right. So I think I said that it depends on the data distribution and how many samples you have. Now, with that said, we also have this result by saying if agent is too weird or has a certain number of data, they might actually trick the system. If you force them to participate, they will exaggerate their gradient. What would that do? If everybody exaggerates their gradient, server doesn't know, server still takes a weighted average, then it's going to move towards that agent's local optimal solution rather than the global one. So that's how agent might be able to attack the system by kind of not really attack, but just kind of steering the system towards its local objective rather than the global one. Okay, so we call that not faithful, right? Something not desirable. So what we want to do here is to design a faithful mechanism where the system can still recover the original system optimality. And also we are going to design incentives so that no agent has the incentive to deviate. Like I was just saying, you might exaggerate your gradient. And we will also satisfy individual rationality, which means everyone would choose to opt in, assuming tie-breaking rule is your will opt in. And also it'll have a budget balancedness, which means the server is not going to inject money into the system. So it's just going to involve payments amongst the agents. Essentially, the high-level idea is the agent who's going to benefit the most from the system will pay to other agents who don't benefit as much, so that once you get paid enough, you will choose to join the system. As a result, everyone's going to stay in the system. Okay, and that is based on a VCG mechanism that's well known from the auction theory. Okay, so all right, so I will try to wrap up in the next 2 minutes or so. And we designed this Faithful Federated Learning algorithm. It's essentially a variant of FedAvg. There's 2 phases now. In phase 1, you run FedAvg for T1 iterations. And then in phase 2 is when we compute the payment. And it's precisely because of phase 2, everyone's being promised this VCG payment, they will faithfully execute the phase 1. Okay, and that's the main idea. And the phase 2 computes the payment according to the VCG mechanism, so that it's there very well-established economic theory to say that this is the individual rational incentive compatible outcome. Now, what is not quite clear is the computation complexity. That's the usual criticism on VCG. So what happens is it takes one agent out of the system at a time and computes the system welfare without the agent compared to the one with the agent in it, and calculates the difference. That's exactly how much that agent should be paying into the system or out, I mean, depending on the sign. Okay, so that by itself, right, you have to take one out, compute something, take another one out, compute something. There is some kind of exponential complexity potentially involved. So that's the usual criticism here. And then in the what we have we're able to show in this particular work is the phase 2 actually does not take that long. The idea is because this phase 1 gets you kind of close to the optimal solution. When you take the agent out and compute the system welfare, you don't have to make that many steps. So either you have a lot of agents, which means removing one doesn't move the equilibrium too much or the optimal solution too much, then you don't have to run that many iterations. Or you have very few number of agents where you remove one would move you a lot, right? In that case, you might run more per agent, but you don't have that many agents to start with. Okay, so in the end, we were able to show the computation complexity is on par with the original FedAvg. Therefore, we can get this kind of faithful mechanism design almost like for free in terms of complexity. Okay, so I think my time is up. Let me just do a quick advertisement for this unlearning work. That's with our postdoc Ningning Ding. She's going to join Hong Kong University of Technology and Science in Shenzhen, and so we looked at what happens when agents could request to leave the system, and how do you handle the incentive for that case. Okay, so I think I'm out of time. Let me just stop here and be happy to take some questions.
All right, thank you so much for fantastic talk. So yeah, so we have a few minutes for questions. So please feel free to ask.
I can ask a question. Hi, Ermin. Thanks for the great talk. So my question is about the generalization part.
Okay.
So you showed two bounds where the epsilon generalization was upper bounded by epsilon, which was the epsilon defined in the stability.
Right. Yeah. Sorry,
bound.
let me
So
go
I
back.
did not understand why this holds the last inequality there.
Yeah, so it's not very straightforward, but you so essentially what you can show is epsilon gen is less or equal to, it's more like this. Epsilon gen is less or equal to that, less or equal to epsilon. That is the inequality that we can show. Yeah.
I see. Okay.
Sorry,
Yeah.
I don't have enough space to go into all the math, but that's the idea. Yeah.
Okay, sounds good. Thank you.
Any other question?
Yeah, I have one question. So, like when you were talking about the results in this generalization part, you mentioned that you, in the federated setting, you showed finite sample bounds, and there was existing work, which I think it was the paper by Woodworth, Patel, and Srebro. So, like I had a question about their work. Like you mentioned that they have results for infinite sample case, but
so that
like
I had a discussion with Nadi about it, so I know exactly what you're talking about. It's kind of subtle, the difference. So they have this equation. I think that's the equation 5 in the paper. Yeah, this is really where the difference is, right? So in our Oh yeah, that work is actually very interesting. So they also get a bound. Their bound, instead, depending on the total variation, depends on the norm of their local objective function evaluated at the optimal solution, like how different that is. So it's also a measure of heterogeneity. Yeah. So we kind of follow their analysis carefully, and I think one of the key steps they had is this thing in the box that I just drew here. Right? They're saying on average, when you are on average, your empirical gradient, the sampled version, is going to be equal to your population one. So even though it's not, they don't explicitly say it's according to infinite sample, but we think you can only get this if you could access the population. Like you could go back and resample it every time. Once you have this kind of a blue histogram to start with, right, then you're slightly biased. Yeah, we still don't have a very tight characterization on like how biased this is convert to the generalization, but I think that'll be a very interesting direction to go into actually. So yeah, we are working, yeah, it's motivated by that whole line, but we wanted to see the polar bear setting when you have finite data sets.
I have one more question.
Okay, go ahead.
There are a couple of
Sorry.
minutes. At the end of this part, you showed a comparison of the three algorithms, scaffold, FedAvg, and FedProx, and the corresponding generalization bounds.
Oh, the bounds. Okay, yeah.
So if I compare those bounds,
Yeah.
is it correct to interpret that scaffold is doing the best among these because of the variance reduction?
That was I asked my group the same question, right? We don't know how to interpret this, and it seems to be the case. But again, it's first off, it's just the upper bound. Secondly, we don't know how tight the upper bound is, right? So under the assumption this bound is tight, then yes, you're right that the scaffold seems to do better, and the intuition, if that's the case, right, the intuition would be maybe the variance reduction somehow helps to generalize better as well. But yeah, I would I would not be there make the claim yet.
Thanks.
Right. Any other question? So otherwise I have a question. So this is a convex case, and it sounded like you also had something to talk about non-convex case.
Yeah.
Can you quickly summarize?
So this is a non-convex case.
Oh.
Yeah, they all have the same structure. Obviously, the coefficients and instead of 1/24, I think we had just 1. So they are different, and also it's not really fair comparison in the following sense. The non-convex case, we were using diminishing step size. The convex case was based on constant step size. Therefore, it might appear the convex case is even worse than the non-convex case. And it means, I guess we can look at here. When you increase step size, the generalization becomes worse. So as a result, it seems we're advocating for non-convex case tends to generalize better. But it's really the when you kill the step size, right? So if you see here, even for FedProx, we were diminishing this eta, which is the weight in front of the prox term. Like that weight is changing over time. And then for scaffold and FedAvg, the step size is diminishing. Yeah. The good news is we could get a bound that kind of looks similar, right? Has a Dmax, has a optimization part, has a part that depend on the sigma. But the not so good news is we still don't know how exactly they would all compare to each other. I mean, other than numerically. I think if anyone can get a lower bound on this, that would be very interesting.
Can I ask one quick question?
Yeah.
So in the convex case, like the generalization error is in terms of the function value difference. Like both the optimization error and generalization errors are in terms of function value difference. So in the non-convex case, like because the optimization error is in terms of gradient norm, so like is the generalization error still in terms of function value, or are you looking at...
we wrapped it all to based on the function value.
Okay.
So you kind of plug it in back in, and yeah.
Okay.
So every time we plug in something, we lose a little bit tightness. As a result, I'm not very confident in how tight this is, but it's in the right direction.
All right. Thank you very much.
Thank you for all the interesting questions and discussions. If anyone's interested to talk more, feel free to shoot me an email.
Yeah, I will knock on your door.
Or that, yeah.
All right. Thank you again for this wonderful talk and discussion.
Thank you for the invitation.